All right. Well, welcome back, folks. I hope you guys had a good weekend. I apologize for yesterday. I had some issues with my computer that I had to work out. I wasn't able to make the recordings for the lecture. So I apologize for that. And hopefully we won't have that issue again. Um, as far as the exam goes, looks like most of you did pretty well. I started grading the exams already. I'll try to have those back to you either tomorrow or Thursday. Okay, so I'll have those posted for you. There's a few of you that have not taken the exam yet. Only one of you have, one of those people who have taken the exam has contacted me. Please make sure you contact me. We need to make sure you get the makeup exam done by the end of this week, or else that exam score will lapse into a zero. So please make sure if you did not take the exam on Friday that you contact me, and that way so we can make arrangements in order for you to take the makeup exam. Okay. All right. So with that said, then let's go ahead and let's get started with the new material here. Now, what I'd like to do today is I want to continue talking. We started talking last Tuesday. We started chapter 12. Make sure you take a look at that material that I posted for you on Classroom for chapter 12. But I want to continue on with chapter 12. And in chapter 12, what we are doing, like I introduced to you on Tuesday, what we were doing last Tuesday, what we were doing in chapter 12 is we are taking the information that we learned in chapter 11, which had to deal with how we can represent chemical reactions in terms of equations. And we're going to combine it together with what we learned in chapter 10, in which we learned how to describe quantities of different substances as well. So what we're going to do in chapter 12 here is we're going to learn how to describe the quantities that are involved in a chemical reaction. So you have to be able to write out the complete chemical equation. You have to be able to deal with the conversions that we dealt with in chapter 10, because in chapter 12 here, stoichiometry is taking those conversions. So this concept, this idea of stoichiometry and what it is in chemistry is essentially taking what we learned in chapter 10 with those conversions and applying it to a chemical reaction now. And a chemical reaction, remember, involves more than one substance. Okay, more than one substance. It could involve multiple elements, multiple compounds combining together in order to form something new. Okay, so what we're going to do is we're going to combine together the material from chapter 10 and the material from chapter 12. So make sure, chapter 11, sorry. So make sure you go back and you review both chapters. If you have any questions, make sure you come by, stop by, folks, and get those questions answered. I'm available after school, 1:30 to 2:30 for your questions. Okay. Today, I may be a little late in getting to the office hours because I have a meeting at 1 o'clock, and so I may be a little late. But please just hold on tight, and I will be there for the office hours. Okay. All right, very good. So with that said, with that introduction, what I'd like us to do then real quick is just work on this problem here. This is a review problem from chapter 10. We are dealing with empirical formulas, okay? Now we're dealing with the molecular formulas here, and we're dealing with percent compositions. You will see this again on the final. And so as we get closer to the end of the semester, I'll explain to you how we will deal with the final, but you will deal with the problem similar to this on the final. And so for those of you who have not taken the exam yet for chapter 10, this will be a good review problem for you to do. And if you are unable to do this problem, please make sure you come by and see me, not only to schedule a time to take the makeup exam, but ask about these questions as well. Okay? And for those of you who have already taken the exam, this will be a good review problem for you to do to keep this information fresh in your mind. And that way, then when you see, if you see this type of problem on the final, you will be fine with it. Okay. All right. So let's take about a couple of 2 or 3 minutes to work on this problem, set it up. Okay. And then we'll come back. When we get back, we'll work on these. We'll work these out together. Okay. So take a couple minutes to work out this problem. Okay. All right. Let's go ahead then and let's take a look at this problem here, where they're asking us to find then the molecular formula for caffeine. So caffeine is that substance, that compound that we consume in sodas, in coffee. Okay, and so we want to find the molecular formula, the actual formula for caffeine. Okay, and what we are given then is we are given percent compositions. And once we are given percent compositions, remember what they want us and they expect us to do with that percent composition is find the empirical formula. the difference between the empirical formula and the molecular formula. The empirical formula represents the lowest whole number ratios between all the atoms in that particular compound, and the molecular formula represents the actual ratios of the atoms in that particular compound. And the molecular formula and that ratio isn't always going to be the same as the ratios that we find in the empirical formula. So make sure you keep that in mind. Okay? All right, so with that said then, whatever caffeine is, caffeine has carbon, okay? And we don't know what the ratio is here, carbon, hydrogen. We don't know what that ratio is either. It has oxygen in it, and it has nitrogen, okay? And so our job then in this particular problem is to fill out that ratio, fill out these numbers here. What's the number that goes here? What's the number that goes here, here, and here? Okay, so we need those numbers to find then the molecular formula for caffeine, okay? That's our goal. What we were given then is we're given percentages, okay? So we're told then that in this particular, caffeine here, caffeine is made up of 49.5% carbon, okay? So let's go ahead and let's start this conversion here. So with that said then, when we are, so we need to find the empirical formula first. In order to get the empirical formula, we're going to get the ratio, the percentages, and basically just say then that that's going to represent the mass, because in 100 grams, whatever this compound is, in 100 grams, 49. If the amount of carbon, the percentage of carbon is 49.5%, then in 100 grams, then we'll have 49.5 grams of carbon. Okay? And so why do we need that? We need that to convert it into moles, because remember, these ratios here represents the ratios, the mole ratios of each one of these atoms, not the mass ratio, but the mole ratio. Okay, so we need to convert into moles. And so therefore, in order to do that, we're going to divide by the molar mass. And so this will be a good chance for us to review also this conversion here, because this is the type of conversion that we'll be doing in chapter 12 here. Okay, so this is the molar mass of carbon. How do we obtain the molar mass of carbon? You go to the periodic table, you find the mass number. We're going to round to the nearest whole number here. You find the mass number and you use that as the molar mass, which the molar mass, and remember from chapter 10, is the mass of 1 mole of that particular element. Okay? All right, so with that said then, let's go ahead and plug that in. And so we end up here with a value of 4.125 moles of carbon. Okay, let's go ahead and do the same thing for the remaining atoms. Okay, so we have hydrogen then. Hydrogen, we were told that it's 5.2%. And so therefore in 100 grams, we have 5.2 grams of hydrogen. Okay. We're going to go ahead and we want to convert that into moles of hydrogen. So therefore we're going to divide by the molar mass of hydrogen here, which is going to be 1. And remember here, we're dealing with atomic hydrogen, not molecular hydrogen. Okay, so that's going to be 1 gram. Right? And so therefore this can be 5.20 moles of hydrogen. The percentage of oxygen is going to be 16.5%, which means then it's going to be 16.5 grams of oxygen. We're going ahead and we're going to convert that into moles of oxygen by dividing it by its molar mass, which is going to be 16 grams. So we're going to divide by 16 here. So therefore we end up with 1.03 moles of oxygen. And then finally with nitrogen, then we're told that it has 28.9, it's 28.9% hydrogen, which means it's going to be 28.9 grams of nitrogen. Converting that into moles as well means then that we would have to divide by 14. Okay. And if we do that, then we end up with 2.06 moles of nitrogen. Okay. All right. So with that said, then right now what we have, and again, this is what we have. This is what we're after. What we have at this point then is we have the ratios. Okay. So we have then 4.125 of carbon, moles of carbon, for every 5.20 moles of hydrogen, okay, 1.03 moles of oxygen, and 2.06 moles of nitrogen. Okay. Now, this looks odd, and it should look odd to you. We can't have, and if it looks odd to you, it means then you understand what these numbers are supposed to represent. Okay, so we can't have subscripts that are fractional in nature, which means that you can't have these decimal places here. Okay, and so how do we eliminate this so that we get the simplest whole number ratios. Well, to start out with then, to get the simplest ratio, we're going to divide all of these by smallest number to get a ratio that would represent the simplest. So we're going to divide all of these by 1.03 because that represents the smallest value of all of these. Okay, and so if we do that, then we end up with carbon here, and it comes real close to 4. Okay, hydrogen here, and when we do this, we can round, and it's going to come real close to 5. Oxygen obviously is going to be 1, and nitrogen then is going to be 2. Okay. All right, so with that said then, once we do that, we see here then that we have a formula. So this formula here represents all these atoms in their simplest whole numbers. This then is your empirical formula. Okay, so this is your empirical formula. So there it is. We have subscripts. We have numbers that are simple. They're whole numbers. Is this? Are we done? Is this caffeine? Okay. Can we just go ahead and plug in 4, 5, 1, 2 here and be done with it? Well, not quite, because what they tell us is this. Okay? They tell us then that whatever caffeine is, okay, whatever its molecular formula is, what its actual molecular formula is, it has a mass of 194.1 grams per mole, which means then when you add up all the carbons, all the hydrogens, all the nitrogens, and all the oxygens, you're going to get a mass then of 194.1. So the question then is, does 4 carbons, when you add that to 5 hydrogens, 1 nitrogen, and 1 oxygen, 1 nitrogen, does it give you a mass of 194.1? Well, the only way you can find out is go ahead and add it up. If you add up the masses of 4 carbons, 5 hydrogens, 1 oxygen, and 2 nitrogens, you get a mass of 97 grams per mole. That's how we know then that this formula here, this empirical formula, does not represent caffeine. That's not your answer there, because this mass here and that mass here is not the same. So then however many carbons, hydrogens, oxygens, nitrogens we have here is more than 4, more than 5, more than 1, more than 2. That the actual numbers here for caffeine is greater than these subscripts here. So how do we find what that is? Okay, well, let's understand this. We know the mass of caffeine. We know the molar mass is 194.1, and we'll just call it 194, okay? And so what's the relationship of this mass here to this mass here? Well, if you take a look at it, this mass here is almost 2 times greater. This mass here, if you double this mass, you're going to get that, okay? Which means then the number of atoms here will be twice as much for, the number of atoms for caffeine will be twice as much as what we have here. And so that means then carbon will be 8. We have twice as many carbons. We'll have twice as many hydrogens. We'll have twice as many oxygens, and we will have twice as many nitrogens. That, folks, is our answer. Okay, so that'll be 8, that will be 10, that will be 2, and that will be 4. Okay, and so if you add up all of those, if you add up 8 carbons, 10 hydrogens, 2 nitrogens, 2 oxygens, and 4 nitrogens, you will get a mass of 194.1. So that is the formula for caffeine. Okay, and that's how you go about doing this problem here. Okay, so please make sure you review this. If you have any questions, come by and see me. Okay, if not, then please make sure then that you review this and make sure you understand what we do. Okay, all right, very good, folks. Let's go ahead then and let's pick up where we left off with. So let's talk about what the stoichiometry is. Okay? So stoichiometry is essentially the study of quantities. Okay, so it's going to be the study of quantities for reactions. Okay? So what it does then, it allows us to calculate for the amounts of reactants and products that are involved in a chemical reaction. Okay, that are involved in a chemical reaction. And so what we're going to do then is we're going to use remember with the equation, you got to balance it. So with stoichiometry then, we're going to take advantage of the balanced equation. So make sure you understand then that we need to have a balanced equation in order to get this done. Okay, so if you don't have the balanced equation, you're not going to be able to do stoichiometry. So stoichiometric calculations involve the balanced equations in which we can use the coefficients. Okay? And so we're going to talk about these coefficients here. So remember, in order to balance the equations, we need to have the coefficients in order to get that done. And so therefore we can use that to obtain the amount of reactants of products. Okay. And so we're going to learn how to interpret these balance equations in terms of the quantities that we want. Okay, so we have to be able to interpret these equations once we get it done. We have to, once we get the balance equation, we have to be able to interpret these balance equations in terms of the quantities of reactants and products that we need. Okay, and so we can interpret those quantities in terms of number of atoms, which we've done already. Okay, we need to be able to interpret in terms of total number of molecules or total number of particles in terms of moles, mass, and volume. And that's what I want us to do today. We're going to talk about how we can interpret these balanced equations in terms of these quantities here. Quantities, and remember, when we deal with quantities, we're dealing with number of particles. Okay, we are dealing with masses of the substances, and we are dealing with volume. Okay, and that's what we were talking about back in chapter 10. So when we interpret these quantities here, when we interpret the reactants and products in terms of their quantities, we should be able to interpret it in terms of particles, in terms of mass, and in terms of volume as well. Okay, so make sure you keep that in mind as we move forward. That's what our goal is. Okay. So let's start out with the simplest one. Okay? When we have a balanced equation, okay, we should be able to, what the balanced equation gives us is it gives us the total number of atoms. So number of atoms on the reactant side and number of atoms on the product side. And we learned that back in chapter 11. Okay, and so make sure you keep this in mind then, that what I want to do first and foremost is if we're going to talk about looking at the balanced equation in terms of total number of atoms, okay, balanced equation total number of atoms, you should just be able to count atoms. That's the whole idea. You should be able to count atoms, and that the total number of atoms in the end on both sides, remember, have to be the same. Okay, so the number and type of atoms should remain the same on both sides there, because that we talked about then the reason why we balance an equation is to make sure then that we can account for the conservation of mass on both sides. Okay. All right, so let's go ahead and let's try one. Let's try a simple one here. Let's take a look at this equation here. Okay, so this is an equation that represents the reaction between nitrogen and hydrogen to form ammonia. Okay, so this is a reaction that involves the reaction between nitrogen, which is diatomic nitrogen, and this is the elemental nitrogen, plus hydrogen. So we are looking at how those two get together to form then ammonia. NHO3 then is ammonia, and that's the cleaning solution that you have in at home. Okay. All right, so let's take a look at this reaction here. Okay. Let's see how we can interpret it in terms of atoms first. Okay, so let's go ahead then, and we're going to do an interpretation of this in terms of atoms. Okay, so let's go ahead and let me go ahead and let's break this out. Okay. Okay. All right, first of all, let's go ahead and sorry. Okay, let's go ahead and let's take a look at this particular molecule atom. Okay, so how many atoms, and again, we're looking at atoms here. How many atoms of nitrogen do we have? Well, this subscript here tells us then that we have 2 atoms of nitrogen. So when we write down, we're going to write down that we have 2 nitrogen atoms, because diatomic nitrogen, elemental nitrogen, is comprised of 2 nitrogen atoms. So 2 nitrogen atoms. Okay. On the reactant side as well, if you take a look at this here, hydrogen then, this subscript here tells us that you have for every molecule of hydrogen, so let's make sure you remember this, nitrogen then is diatomic. Okay. We talked about that with the Lewis dot structure. Okay. And then with hydrogen here, okay, we have each hydrogen molecule is a single bonded. Okay, so you have 2 hydrogens for every 1 molecule of hydrogen. But for the balanced equation, then the subscript here tells us that we have 3. So if we have 3 of these molecules, okay, we have 3 of these, we have a total of 6 hydrogen atoms. Okay, so make sure then you remember how we get these numbers here. Okay, so 2 nitrogen atoms, 6 hydrogen atoms to start out with. So we have a total then of 8 atoms. We add it up, 8 atoms on the left-hand side for the reactants. On the right-hand side, what do we have here? Well, we have ammonia, which is, and again, the Lewis dot structures here, make sure you remember how to draw these. Again, we have then one ammonia molecule that has 3 hydrogens attached to 1 nitrogen. That's what this tells us right here. Okay, that the single molecule here has 3 hydrogens and 1 nitrogen. This coefficient here tells us that we have 2, that when this reaction runs, we're going to form 2 of these ammonia particles. We have 2 of these here. So in 2 of these here, we have then a total of 2 nitrogen atoms that will form 2 nitrogen atoms, okay, and 6 hydrogen atoms that form, okay. And again, if we total up everything here, we have then 8 total atoms as well, okay. So essentially, when we interpret, and I'm sorry, let me just go a little bit longer. When we interpret this reaction here, so the reaction we're looking at is the reaction between that I introduced you in the last one, the reaction between nitrogen and hydrogen, 1 nitrogen with 3 hydrogens to form 2 particles of ammonia. When we have that, then we start out with 2 nitrogen atoms, 6 hydrogen atoms. We end up with 2 nitrogen atoms, 6 hydrogen atoms, so that the total number of nitrogens, total number of hydrogens should be the same, and the total number of atoms should be the same as well. So the number and type of atoms must be the same on both sides of this chart here, of this table here, okay? Because whatever you start out with the reactants, you should end up with that in terms of the atoms, okay? All right, so make sure you're able to do that, folks, because what I'd like to do tomorrow is I want to continue on, and I want to get right into this discussion here of what else can we do with a balanced equation like this? What else can we do in terms of interpreting it to help us then when we start talking about chemical, how we can start doing the calculations involved in this, okay? So please take a look at it, read a little bit ahead so that tomorrow then when we start talking about interpreting chemical equations, we can go a little bit more quickly, okay? All right, very good. So please make sure you submit the work that we did from above, just towards the beginning of class. Make sure you submit that, okay? And then read ahead a little bit. And if you have any questions, come by and see me today after school. And if not, I will see you tomorrow, okay? Have a good day, folks.